Good morning, everybody. Welcome to our class today, Friday, March 5th, 2021. We'll continue where we stopped yesterday. We took the handout 6, and we talk about push-down automata and pumping lemma for context-free languages or context-free grammars. As I mentioned yesterday, that the push-down automata, in a simple form, it is an epsilon non-deterministic finite automata in addition to a stack. Stack, as we said, has two operations, either push or pop. Push will add an element to the top of the stack, and pop will remove the topmost element of the stack. Stack, what is the stack? Stack is a linear data structure that you can access only from one end. You cannot access in both directions. Only because if you can access from both directions, it will be called a queue. Only the topmost element can be accessed at a given time. Only I can access this top element. I cannot go to the middle before popping out all the element before it. To access intermediate element, all elements above it must be popped. A push-down automaton has an input tape here, input tape, and a finite control which contain a set of states, and unbounded stack. What do we mean by unbounded stack? That the stack has no limit in size. I can add as much as I can string. So in state, let's say Q, I read a simple AI, then if the operation set to push X, X will be in the top of the stack. This is the push down automaton in kind of figures. At any given point of the time, the push-down automaton PDA is in some state at that time, should be in some state P, reads some input simple AI, access the topmost element of the stack X, either push or pop. The PDA at this point can move from state P to Q, can change the topmost element of the stack from X to Y, for example. This will be represented that we'll put the P, the name of the state, what is the symbol read, and what we will push on the stack, and what will be replaced, which state I will be, and what is the symbol that I push it in the stack. We allow the stack to have a different alphabet, usually denoted as, yesterday I said row, it's gamma capital in Latin. So this is gamma, capital gamma. Given an input W, the PDA at any given instance does the following. We talked all about this yesterday, and I'm repeating this in the class note. We will read AI from W, where AI belongs to sigma epsilon, goes from state P to Q, replaces the topmost element of the stack X with Y, where X and Y both are element of the stack alphabet. Gamma epsilon, it is the stack alphabet. What does this mean? What does this mean for X to be an epsilon or Y to be an epsilon? If X is an epsilon, then we're pushing Y on the stack immediately. We don't need to pop anything. If Y to be an epsilon, popping out X from the stack. We have to take out X from the stack. So, for example, if I'm at state P and I read AI and I have X, then I'll read, it asks me, for example, to either leave X and become below Y or pop it out, doesn't matter, depends on the state. So I move from state P to state Q. The pointer now at symbol AI plus 1, the next symbol, and Y become the top of the stack or the topmost element. Example, formal definition of the PDA, we have it yesterday in handout 6, slide 6. Due to the non-determinism characteristic of the push-down automaton, there can be multiple transitions on the same tuple, P, AI, and X. And we will see some example, we'll make some branches, because I have two scenarios, case 1, case 2. So we can go in both directions. So the transition denoted, I'm at state P, I read AI and there is X and replace it with Y and I move to Q. As we saw yesterday, that the PDA consists of a tuple Q, which is the set of states, sigma, which is the alphabet, gamma, which is the stack alphabet, delta, which is the transition function, and the Q naught starting state, and F is the accepting state. Is said to accept a string W that belongs to sigma star if there exists a sequence of symbol A1 to AM that belong to that alphabet, state R0, R1 to RM that belong to Q, and a string S0, S1 to SM that belong to the gamma star, which is the stack alphabet. Such that W, it's a full string, consists of different symbol from A1 to AM. R0 is a Q naught, and S0 is epsilon initial condition for the stack. For every I, if Riy belong to delta, which is the transition function of Ri minus 1, Ai and x, then Si will become the Yt. T, here we represent the remaining of the stack. T, here in our drawing, means the remaining stack contents. For some T belongs to gamma star, and XY belongs to gamma epsilon transition condition. Rm, when I reach to Rm, which is belongs to F, which is the final state or accept state, we are at accept state. Otherwise, reject. Here in a vector form, like X, T is the remaining of the stack before the step. After doing the step, Y becomes the top of the stack, and T is the remaining stack contents after the step. So let's have an example, same as our example yesterday. I will repeat it so to make sure that everybody is understanding it. Given that the PDA, pushdown automata of the language, L 0 to the power n, 1 to the power n, where n is greater or equal to 0, I'll start at start state Q naught with epsilon transition. I will push a hash in the stack. This, if you remember, in our handout, we use the $sign. You can use any symbol for you. This symbol will let you know that I reached to the end of the stack. The stack now is empty. So if I receive a 0 with epsilon, I will push an A to the stack. Now then, after finishing the zeros, I will use epsilon transition to move to the 1 part. Then if I read the 1, I'll pop A from the stack and replace it with nothing till the thing is A. If I reach to the hash, I have epsilon as an input, and I have a hash at the end of the stack. I'll pop the hash and leave its epsilon, which is empty stack, then accept. So let's think about this example. If we have a sub example, like if I give you a string that's saying O to the power 2, 1 to the power 2, does this PDA accept this string? We will see. At the beginning, nothing. We are at a Q naught, and the stack content are epsilon, which is empty. Then I'll use epsilon as an input. Then I'll do an epsilon transition to push the hash, and I'll move to Q1 here. You see epsilon, epsilon hash. I'll move to Q1 here. Then I will read the first 0. The first 0 saying 0 with epsilon push A, and I stay at the Q1, then the stack content will be A hash. Then I will read the second 0. I'll do the same, then I'll push A hash. Then I'm done with zeros. I'll use epsilon transition to move to the next state. And I'm at the Q2 that time, and I will read the first one. I'll pop out an A. You see, after the arrow, which means push, before the arrow means pop. Because sometimes the student confused when they're solving the question. After the arrow means push, before the arrow means pop. Remember it like this. Okay, so 1A epsilon. I'm still at the Q2, but the stack content is A because I pop 1A, A1. Then I read the second one and I pop the second A, and I'm at hash. Once I read hash, that means move me to Q3 and accept the string. If we take another example, which will not be accepted, if I took O2, 1, then I read epsilon, I push the hash, then I read the first 0, the second 0, then the stack content will be A hash. Then I read an epsilon and move to the 1 part. I read 1, I push 1A, then the stack content is A. At that time, I will stack and the string will not be accepted. Okay, let's have more sophisticated example to make sure that we cover the parts of push-down automaton. Now, assume that we have the language L, which consists of three symbols A, B, and C, and the power of A is I, B to the power J, C to the power K, and I have here two scenarios to accept. If I equal J, which means if the number of A's equal the number of B's, then accept, or the number of B's should be equal to the number of C's or double the C's. Make it a bit complex. So I have here two options. Either I will check the number of A's and B's. I don't care about the number of C's, whatever the K is, I would accept. Or if this is not the case, then I have another case that I will check the B's and C's, and the number of C's should be as minimum equal to the number of C's, or as maximum double the number of C's, or in between. So okay, so at the beginning, during the non-determinism characteristic of the push-down automata, I could start from the initial state and go into two branches. And we see in NFA, we go different ways. So with epsilon transition, either I took this route or that route, we will decide, we will push the hash to the stack, which is the initial state or initial step. Then I will read the A's, and at each time I'm reading the A, which will be the same as 0 to the power n, 1 to the power n, because they are equal. And this is what I'm caring about. So at that time, I will read the A's. Each time I read A small, I'll push an A to the stack. Then the next step, when I'm reading the B, I'll pop an A. And once we reach to the hash, whatever we read the C, do nothing and accept. This is the first scenario. The second scenario, which is the other condition here, I will read A's because they don't care about A's, and I will do nothing. Then the issue with B's and C's. And here I have two scenarios. Either with each C, I'll pop two B's or one B, because you see the number of C's are in between. Could be this, could be that, or in between. So how we will decide how to pop one or two. So here we have another scenario we have to follow. So once we read the B, we'll push a B. Then when we read the C, we'll push a B, which is one. Or if I want to pop two B's, I'll go this way. I'll pop B. Then when I back, I'll pop another B. Once we are done and we reach to the hash, we'll go to the accept state. Is that clear, guys? This is the push-down automata for this language. Clear? Questions before moving to example 3? Okay. With example 3, assume that L2, a language that consists of a string W. W belongs to A, B star, where W is the reverse of W. Okay, you will ask me here a question. When I will start to push, then when I will do the pop. The thing here is at the center or the middle point of the string. If it's even or odd, it will be different. If it's even, the middle two symbol, I will do nothing for them. But if it's odd, I will just leave the middle. For example, if I have a string A, B, 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 A. So the second B is in the middle. But if I have A, B, A, B, A, B, the middle A, B will be the middle of the string. So I'll take both scenarios. we will push the hash, and we have two states, Q push and Q pop. Q push A's, and if I read B push B, once I'm done, either I'll go to start popping them to reverse the string, and if at the middle point, if there is the middle point is B, do nothing, or A, do nothing, or both, take them both, then move to the transition, and at that time we are reversing the string. Clear? So that normally when you have a question, consider different scenarios. Clear, guys? Okay. So let's go to 9. Okay. We talk in the second part of the handout about the parse tree. It is a simple topic, but we will talk about it again. Let G be a CFG, context-free grammar, and W is a string that belongs to that grammar. A parse tree of W with respect to G is rooted ordered tree. What do we mean? Rooted ordered tree. We will see how that represent the derivation of W with respect to G. And with respect, we will use WRT from now. So, example, if we have the grammar G, which take the example that we took, which is 0 as 1, and we have O to the or epsilon, O to the power 3 and 1 to, or 0 to the power 3 and 1 to the power 3. Parse tree of W with respect to that grammar is S will be replaced with 0 as 1. Then we have a 3 here. Then 0 as 1. Then 0 as 1. At that time, I have 3 zeros and 3 1s. Then we'll go to the epsilon. So every internal node is a variable. Every leave node is either a terminal or epsilon. If it's epsilon, then it is only child of its parent. If an internal node labeled R and A1 to AK are the childest of R from the left to right, then R. So how we will read it? 0, 0, 0 from left to right. Concentration of the leaves of a parse tree from left to right gives the string W. Now, example 2, if we have 0 as 1 as or 1 as 0 as our second example yesterday. So here we have S, which will replace it with 0 as 1 as, and the first S we will replace it with epsilon. Then, because we have this string, then we have 0, 1 now from the left. Then we will replace S with 0 as 1 as. This one will be epsilon. Then it will be 0, 1, 0, 1. And here we have the other one, which is 1 as 0 as, and we replace those with epsilon. So we read it 0, 1, 0, 1, 1, 0, 1, which is our string. You see how we read it? From left to right. So you see here 0, epsilon, 1, 0, it's a parse tree of W with respect to G. This is the second parse tree with respect to G. We can do it this way. So you can do it whatever you want. We can have multiple parse tree for some string. So some string, it might be different in the parse tree. However, if it's let me arrive to the accept state, then we are okay. There are many multiple parse trees for a string with respect to a grammar, like 0, 1, 0, 1, 1, 0. With respect to G2 also, it is accepted. Question. What about G1 can be multiple parse tree? This one, I'm asking here. This is G1. No, we cannot have multiple. But the other example show you that we sometimes we have. So let's make unique variable 0 as 1. On the other hand, G1 has a unique parse tree for every W belongs to L in G1. The derivation of a string with respect to a grammar G is a sequence of a substitution that yields W. So if we have W O square 1 square with respect to G1, then we'll have 0 S1, 0, 0 S1, 1, 0, 0 epsilon 1, 1 has only one derivation. Second derivation, 0 S1S, 0 S1S, 0 S1SS, and it will represent this way. Now we'll come to your friend pumping lemma for CFL. Guys, the same concept, but now with 5 simple. We split the string to 5 symbols. U, V, X, Y, Z. Before, we use X, Y, Z. It's the same concept. But here we'll add the power to the V and Y. Or if you use VU, it will be for the U and the Y. Now, let L be a context-free grammar and G be a CFG such that L equal L of G. Let W belong to L of G and let T be the smallest parsed tree of W with respect to G. With regard to T, if the maximum degree of T is D and the height of T is H, then the length of W is less or equal D to the power H. So this is the parse tree if T, and here we have the height, and we use these things. By pigeonhole principle, there exist 2 nodes labeled with the same variable, say R. Here, we have R and R. In the last, V plus 2 nodes. So here, X, V, X, Y less than D. You know, we don't need this proof. I just write it for you to understand how we come out with pigeonhole principle. Both V and Y cannot be the empty string. V and Y cannot be the empty string. Same as in non-regular languages, we said Y cannot be an empty string. X could be, Z could be, but Y no. Here with context-free grammar, we have two strings that should not be empty, V and Y. And here are the derivation. I'll not go through that. We'll start solving here. U, V, V, A, V, Y, 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 Z, V, X, Y. So U, V3, X, Y3, Z belong to L of G. Now, we will state pumping lemma theorem. Pumping lemma theorem, the same thing as before, but here we'll have U, V to the power I and Y to the power I should be belong to L. And set P equal D to the power V plus 1. Note that P only depends on the context-free grammar that we choose for L. Now, assume this example. If L is A to the power N, B to the power N, C to the power N, given P greater or equal 0, choose W equal A to the power P, B to the power P, C to the power P. A given A apportion W, U, V, X, Y, Z, such that Vxy less or equal to P and Vy greater than 0. The length of V and Y is greater than 0. Choose I equal 0. Let Vy equal K. Analyze the string UXZ. Case 1. Now here in our example, in case 1, string Vxy consists of one symbol. Vxy cannot only one symbol, contains only one symbol. Say that Vxy consists of A's. Then Ux equal A to the power P minus K, B to the power P and C to the power P, where K is greater than 0. So UXZ is not belonging to L from the beginning because we have a different power here. They should be the same. Case 2, Vxy has two symbols only, and let Vxy consist of A's and B's only. Then Uxz equal A to the power K1, B to the power K2, C to the power P, where K1 and K2 less than 2P, then Uxyz is not belonging to L. The same principles, guys. Vxy cannot contain all three symbols, A, B, and C, as Vxy less than P, so L is not a context-free language. Another example. If we have the string WW, where W belongs to sigma star, assume sigma equal A and B. Choose W equal A to the power B, B to the power B, and A to the power P, B to the power P, because we have WW. Given a portion W, X, U, V, X, Y, and Z, let the length of Vy equal K and greater than 0. The case analysis. The first case, Vxy consists of one symbol. Suppose without loss of generality, Vxy is contained in the first block of A's. Choose I equals 0. So uv to the power 0, xy to the power 0, and z. Then it will be a to the power p minus k, b to the power p, a to the power p, b to the power p, which is not belong to that language. Case 2. If consists of two symbols, a's and b's, then a to the power p, b to the power p, a to the power p, and this is vx and y. Choose I equal 2. So uv square xy square z square, which will be a to the power k1, b to the power k2, ab, ap, where k1 and k2 is greater than 2p's. And this is not contained in CFL. Same principles, guys. Same principles. More examples of pumping lemma will be solved in next week tutorial with the TA. Any questions? Okay. So we'll move Turing machines. We'll take the handout, and next class we will do the class notes. What is a Turing machine? We have finally arrived at the complete of the model of the computation. This is the last model of computation, and graphs and context-free grammars and all of these things. We finally arrived at a complete model of computation, Turing machine. Turing machine capture a model of computation that has full effective range of computational power. If you compute it, there exists a Turing machine that can compute it. Fundamental limitations, even a Turing machine cannot solve some problems. Even Turing machine, even it's a powerful computational model, however, sometimes there are some problems that could not be computed using Turing machine. So, Turing machine consists of the following components. Tape is an infinite tape of memory cells, head to read and write, head pointing a single memory cell on the tape. The head can move left and right. Here in Turing machine, we can go left and right, not like the stack. We can access only from one direction. Control, a finite automaton that control movements of the head reading from and writing onto the tape. It has explicit accept or reject state, and the Turing machine stop halts, we call it, whenever reach one. Technically, the tape is not infinite in both directions. It has a beginning, but continues forever. Initially, the input string appears on the tape starting at the beginning. All cells beyond the input are marked like with this symbol, meaning empty. If you see this symbol, this is meaning empty.
So I have a quick question regarding the tape. So essentially, let's say we are at the middle, but we have, so let me rephrase it. So we have 20 memory cells and we want access 10. Would we have to go one by one?
Yes, it's a tape.
Okay. So essentially speaking, it's like stack, but without getting rid of the part at the top. So we can just
Yes,
access it.
you can go left and right,
Okay. But essentially
but you have
speaking,
to move one memory cell at a time.
okay, it's not like, okay, gotcha.
You know, yeah, I need you to imagine. Do you know the normal tape that we used here in 90s?
Yes, the
So if there is a
plastic
song
tape.
at the middle, you have to make forward all the way till you reach it.
Okay.
It's the same.
In order to call the function, would we have to, I guess, so my question is it possible for us to specifically find a value without actually using the tape? Like, is there a
No,
possibility?
that will be direct memory access, which is different concept.
Okay.
Yeah. Okay. A Turing machine is essentially a finite automaton with the ability to read and write from a memory tape. This is the extra thing that give the computational model more power. As the Turing machine reads character from the tape, it may move its head left or right and may write a new character to the tape. So it has these left, right, read, or write options. Turing machine example. A Turing machine erasing the last symbol on the input. If I have, this is the Turing machine, the tape is at A, step 1, not blank, move right. Okay, B, not blank, move right. Then I see here a blank, move left back. Once I move left, I remove the last bit. Here how it's working. Turing machine definition. In order to be more self-consistent with the definition of NFAs and PDAs and to make your life a little bit easier, we'll follow along the lines of the Peter Lenz definition of Turing machine instead of Spicer. See comparison here. If you press here, you will see the difference. The difference of definition of Turing machine between Spicer and Peter Lenz. Peter Lenz is a bit easier, okay? Tape may extend infinitely in either direction, and the read head is free to move beyond the input in either direction. Instead of having a single final accept state, you may allow F belong or equal to belong to Q to be the set of accept states. So Peter Lenz allow us in his model to have more than one accept state. Instead of having a single explicit reject state, you can assume like in NFA and PDAs that input is rejected if there is no transition out of the current state. You may leave it to faith or to an interpret Google search that two definitions are essentially equivalent. They are equivalent. However, the Lenz definition is easier for you to understand. So the Turing machine is a six-tuple Q, sigma, gamma, delta, Q naught, and F. Here a finite set of state. This is the alphabet, not containing a black symbol. The black symbol is a symbol used to show that this memory cell in the tape is empty. So it's not part of the language of the alphabet. A tuple alphabet where the blank is belong to T and also the alphabet, the normal alphabet is belong also to gamma. Delta Q times gamma will send me to a new Q or to new state with gamma and with the where to move, left or right, I have to know. Q naught belongs to Q, which is the start state, and F is the accept state. String copy. Recall the string copy that we took it in handout 6. And we said that the push-down automata cannot deal with this kind of examples. Recall the pumping lemma that L is not a context-free. We proved that L is not a context-free for WW just now. Meaning there is no CFG that can generate this language, or similarly a PDA that can recognize it. Let's now see how a Turing machine is able to recognize this language. As a simplifying assumption, let's assume there is a delimiter hash between the two substring. Move back and forth across the tape to matching position on either side of the delimiter. If the symbol do not match or no delimiter is found, reject or halt, we call it in Turing machine. In order to keep track which comparison you are made already, cross out the symbol on the tape example by replacing a symbol with X. When all symbols on the right of the hash have been crossed out, check if there are any uncrossed symbol left on the right. If so, reject, otherwise accept. Here. So the notation A is used to denote the current location of the head. So here we have this one, and we will start, and this is the hash. Begin, cross out the first one, cross matching position, find. You will keep crossing till you reach to this point. If there is no uncrossed cells, then accept. Okay. State transition. Let's draw the state transition diagram for L. See example 3.9 in your textbook. This will draw the state transition. And next class, we will have the class note with more example. Also, the TA will give you more example on this. Related languages. We saw strategy for recognizing L. What about arbitrary copies? If we have multiple W's. Recall we approved that this example, A to the power I, B to the power I, C to the power I is not a context free. But with Turing machine, we can follow the strategy of moving back and forth, crossing out symbol and corresponding position. And like the string copy example, we can design a program to count arbitrary non-infinite copies. The multiplication. Let's see a Turing machine performing multiplication. Remember, in our model of formal languages, we are not computing the answer k to input I times j, rather than we inputting I, j, k, and recognize the language where I times j equal k for simplicity. We will use unary representation. Let argument 1 be I, repetition of A, argument 2 will be J, repetition of B, and argument 3 will be K, repetition of C. The language will become A to the power I, B to the power J, and C to the power K, where IJ equal K, and IJ K greater than 1. Also for this one, see the example number 3.11 in your course text. Okay, guys. Questions? You have to read. Next Friday, we have a quiz, and presentation will start on Thursday. We will have the Turing machines, class notes. It will not be that much. 3, 4, 5 pages. There are only 5 pages, the class notes. We'll finish them in 10-15 minutes. Then we are ready to move to handout 8, which is here we finish our computing. Then we'll move to handout, which is decidability and the church Turing thesis. We'll start talk about the language hierarchy again. Then we'll talk some issues in simple way. We'll not go deep details. Then in handout 9, we'll go universing Turing machine, halting problem, and the existence of undecidable languages. We'll talk about these problems. This will be the longest remaining handout. 10, 11, and 12, we'll finish them in one class. They are not that much. We all must around 2/3 of our course. And here we'll just take, we'll not go in deep details with complexity and hard and P and BPP. So the remaining is a bit easier than what we got before. If you don't have a question, I will stop recording here. See you next week. Good luck. Have a nice weekend, guys. And tomorrow morning, I will release assignment 3. Good luck and bye-bye.
Have a good day, sir.
You too. Thank you, Steve. Thank you. If you have a question, you can stay. Also, to make your life easier, I will upload the video today. I find a way to quicker upload it in YouTube. So it will be uploaded today. Questions, Zach, Yudi, Logan? Ariana, do you have any questions?